An average sailboat goes at around 6 knots. A bulk carrier goes twice as fast, and cruise ships and ferries, they reach up to 25 or even 30 knots. But what even is a knot? This is How Ships Work, a series in which I explain the complexity behind modern ships and the perfect harmony between different systems that empower over 80% of global trade. Now, answering the question about the ship's speed is not as straightforward as one may think. In cars, for example, the faster the wheel spins, the faster the car goes. On ships, it doesn't really work like that, because the ship is moving the water by turning the propeller, but there's a ton of different forces that can change the outcome. So, turning the propeller twice as fast doesn't necessarily mean that the ship will go twice as fast. The first method ever used by seafarers to tell the ship's speed was simply throwing a wooden log overboard. They would throw it at the bow and then count how much time it would take for the wooden log to reach the stern. It wasn't the most accurate way to tell the speed, but it was the only one available at the time. It was in 1574 when William Byrne for the first time made a historical record of a log and line method. Now, instead of just throwing the log overboard, the seafarers would attach a line to this log, and then on the line they would tie knots at regular intervals. As the log was thrown overboard, it would catch in the water and remain in the same place. As the ship sailed away, the line would unspool, and a sailor would flip a sandglass and count the knots on the rope. The moment the sand ran out, they would stop the line, and the number of knots that had passed would indicate the ship's speed. The invention of log and line method made knots a standard unit of speed at sea, but it took many more years for one knot to become the same all around the world. In 1594, an English mathematician, Robert Hughes, was one of the first to describe the nautical mile, and his definition is still used nowadays. On charts, the globe is divided into 360 degrees, and each degree is divided into 60 minutes. Robert Hughes was the one to define nautical mile as exactly 1 minute of latitude. At his time, 1 nautical mile was about 5,000 feet. The seafarers would start using standardized sunglasses that would count exactly 30 seconds and knots spaced every 42 feet. As time elapsed, the Earth was measured with better tools and better accuracy, and the nautical mile was corrected many times until it finally settled in 1929. That's when it finally settled at 1,852 meters or 6,076 feet. An electromagnetic log, EM for short, uses a magnetic probe mounted below the ship's hull, and the water passing by that probe is generating tiny voltages that are exactly proportional to the ship's speed. Now that we've defined knots and nautical miles, it's important that I also tell you about two different kinds of speed that we use on ships. As you may remember from your science class, the speed is relative. For example, when driving a car, I'm not moving at all compared to the car itself. My speed is equal to 0. But compared to the ground or trees that are around me, I am moving at really high speeds. While it's not very important while driving a car, it makes a huge difference on ships whether we are comparing ourselves to the water or to the ground. The speed through water is the speed of the water flowing past the ship's hull. This speed is very important for maneuvering because as the water speed reduces, the ship loses its ability to make turns. The speed over ground is important for calculating actual distances and times of arrival. This is the speed that we use for logistics. Now, to better understand the water speed, let's imagine a ship on a completely calm sea with no currents and no winds. Her speed through water and her speed over ground will be exactly the same. Now let's imagine she enters a river and goes up against a current of 3 knots. Her water speed will still be 6 knots because she is pushing just as hard, but her ground speed will drop to 3 knots because the current is slowing the ship down. Now when the same ship turns around and goes with the current, her ground speed will increase to 9 knots and the water speed will still remain at 6 knots. So far, all the logs covered in this video only measure the water speed. Now, to measure the ground speed, you need some point of reference other than the water or things that move with it. So you can use the seabed or some points on shore. While the EM logs created a new standard and the captains could finally see their speed in real time on the bridge, it wasn't until 1970s when the Doppler logs were launched that truly revolutionized the industry. EM logs are terrible at low speeds because they rely on the water flow. At similar time, the ships grew exponentially, from 20,000 tons of cargo to 200 tons of cargo. And the bigger the ship, the more accuracy it requires to even maneuver in tight ports. The Doppler log, as the name suggests, uses the Doppler effect. You know this effect, for example, from an ambulance passing by. As the ambulance approaches, the siren pitch is really high, and as it passes you, the pitch drops to a lower frequency. Instead of sirens, the Doppler log uses ultrasounds. It sends those sound waves towards the seabed, and when the ship is stationary, they come back unchanged. But when the ship starts moving, there is a noticeable change in the frequency. Now, the reason why the Doppler logs are so important is because they no longer use water as reference. Instead, they use the seabed. Of course, it was possible to tell the ship's speed over ground before, but it required taking position twice, then measuring distance and time, and it couldn't be done in real time. The reading from a Doppler log is actually speed over ground, but there is a catch. When the ship sails away from the shore and the depths exceed, for example, 200 meters, the sound waves can't reach the bottom anymore. The sound waves reflect now from plankton and other things that float below the water surface. So what we actually measure is the speed through water. In harsh weather conditions, the ship moves up and down on the waves. This would impact the readings, so the engineers added a second transceiver that sends the sound waves in the opposite direction to the primary one. Now, any error in the ship's vertical movement would be cancelled out between the transceivers. For the larger ship, it's not only important to know how fast we're going forward, but also how fast we are moving to the sides. It's especially important when mooring. And for this reason, the Doppler logs usually have 4 transceivers now, 2 pointing forward and aft, and 2 pointing to port side and starboard side. Even though the Doppler logs were really exciting, soon GPS was released to the general public, and now both electromagnetic and Doppler logs are just used for redundancy. They simply serve as a backup in case the GPS malfunctioned, or they are used to tell the water speed during the port maneuvers. The GPS calculates the ship's position many times in a second, so it can just simply take the distance and time between those 2 points and give us live reading of course and speed. Of course, the speed given by the GPS is referenced to the ground. The GPS receiver is by far the most important instrument that you can find on a navigational bridge. Even though it seems really simple, it can trick you just as easily. And that's what happened on the Queen of the North that I covered in the first episode. On ships, everything can trick you if you don't know how to properly use it. That's why I made this series and teach you in every episode how ships work.